In this problem, we have a plane that is moving with an initial velocity. Our v naught is 100 miles per hour. And what our plane is trying to do is it is trying to drop this crate of supplies onto this desert island where this person is trapped and needs help. So we know there's two things we know. We know that one, we're moving to the right at 100 miles per hour, and two, our distance above the water to our plane is 500 feet. And since this is a projectile problem, when we drop this supply crate, the only force that is acting on it is the acceleration, which is gravity. So our acceleration is equal to gravity, and this is equal to minus 32.2 feet per second squared. And let's just do a conversion right now. Our 100 miles per hour is going to be equal to 146.6 feet per second. So now that we have our initial x velocity, our v naught x, it's 146.6 feet per second. Our initial y velocity is going to be 0 feet per second because our plane is only moving in the x direction. And we are going to define our positive y to be this way, our positive x to be this way. So right here, this is our origin, which is where our supplies are dropped from. And the plane right here is at 500 feet. So our y naught is equal to 500 feet. And our x naught is equal to 0 feet because it starts at x is equal to 0. So how do we find the distance that we have to drop this crate before we reach the island? So this distance right here, so the supplies fall on the island and not the water. Well, first we have to figure out the amount of time. We have to figure out the amount of time that the supply crate will be in the air. And if we look at all our equations, we sort of realize that we should look at our vertical components of this problem first. So we have a change in height, and this change of height will govern how long the supply is in the air for. This along with gravity. So we have this y naught, or this our final y position is equal to an initial y position plus an initial velocity in the y direction times time plus 1/2 times the acceleration times time squared. And we know all of these pieces of information except for time. We know that we have no velocity in the y direction because it's only in the x direction. So we can cross that term out. And we also know that our final y position is going to be 0 feet because that's when the supply hits the island. So 0 is equal to, our initial y position is 500 plus 1/2 times our acceleration, and our acceleration is minus 32.2 times time squared. And when we solve this equation out, because this is a squared term, we're going to get two roots for t. We get t is equal to minus 5.572 seconds, and we get 5.572 seconds. And we know that since this is a time and what this problem is asking for our application, this route doesn't make sense, so we can cross it out, forget about it, and we know the package is in the air for 5.572 seconds. Now that we know the package has been in the air for 5.572 seconds, we need to figure out this distance, the total distance it's moved in the x direction. So if we look at our horizontal equations, we know that our final x position is going to be equal to an initial x position plus the velocity in the x position times time. And we know all these pieces of information except for what our final x position is. So if we fill in what we know, we have 0, so this term just sort of goes away, and we have x is equal to our velocity in the x direction, which is 146.6 feet per second, times our time, and our time is 5.572 seconds. And if we perform this multiplication, we're going to get that x is equal to, so x is equal to 816.6 feet. And what does this mean? This means that when we are 816.6 feet away from this island, we need to release the supplies so it will hit the island.